Last time we were talking about, we finished up on electronic materials or chip attachment, and I talked about controlled collapse chip connection, which is called C4, or sometimes called area array. And because you're doing area bonding rather than perimeter bonding, you can in principle get up to 1,000 to 2,000 input-output leads. In fact, you don't really get that many because you can't use the whole surface area of the chip. Even though it's only a square centimeter or so, it turns out because of the thermal expansion differences, you have a hard time using all of the ones on the outer edges and stuff because there's too much shear going on. Plus, it turns out over the last few years, as we've gotten more and more chips or transistors on a chip, we really don't have to get we've kind of broken down in Rent's rule, and we don't have to get 1,000 to 2,000 IOs. Some people would still like to for certain types of chips, but in most cases we're putting lots of chips on a single chip because we can get so many transistors on a chip. And so we kind of have started to limit out around 400 IO for common things. I also found some of my overheads that we talked about wire bonding, and I talked about kind of a little sewing machine needle. So you've got this little head, which they call this is ultrasonic wire bonding, which they call a sonotrode because of the ultrasonic vibration to help the wire bonding. And it's basically a little metallic needle, if you will, and it's got the wire fed through it, and it comes down. Apply ultrasonics in this case, and you end up making a wire bond on a pad here, and then it comes over, makes another one. They can only make about 7 a second, okay, of these bonds. So this thing's humming along pretty fast. And basically it's limited by the inertia of the system. You just can't move that mass much faster and still have precision. You start getting all kinds of dynamics and stuff. This is the, and you've got a handout with these things in them on chip to package interconnection, so far as that goes. These come out of one of those, comes out of this handout on chip to package interconnection. So this is the thermocompression bonding. You got a gold wire, and again a little sewing machine type of head, and it comes in and just squeezes the whole thing and gets the interfacial sliding by the pad here. In some cases they use a little hydrogen torch to melt the tip. Typically that's for the aluminum wedge bonding. You don't usually have to do that for gold, but sometimes with gold they do it as well. And you make your bond, and then you make the bond here, and then you come over and make another bond on the other side. So you got these little loops of wire, whether you're using the ultrasonic wire bonding or whether you're using the sonotrode. Another example, I had talked to you, and I had actually shown you the following. I had put up on the board this graph, which shows this is the oxide to metal hardness ratio, and this is the indium and the aluminum and the tin. This is the percent deformation. You also have this handout so far as that goes. And I mentioned that aluminum was essentially the second easiest material to cold weld because it has such a high hardness to its metal oxide, and pure aluminum is relatively soft. And because of that, basically when you squeeze and get some interfacial sliding, the aluminum oxide doesn't smear like peanut butter across the surface and recontaminate the surface. It stays there as hard lumps. Well, it turns out people actually weld aluminum wire together in the aluminum wire drawing business. This comes out of the welding handbook. I think you've got a copy of this, but it doesn't really matter. You can't just push two wires together to bond them because you don't have any interfacial sliding. So what they actually do is they have some dies that hold the wire, and they kink it sideways, and they squeeze it once, and so you're now getting interfacial sliding because the two are at kind of a funny angle, right? So you squeeze them together. Now you're getting interfacial sliding. You then take that and you do it several times, so you get more and more interfacial sliding, and you can essentially make near perfect welds in aluminum wires by cold welding. We can't do that with iron or copper because we just can't get enough deformation in wires when you have small little ends like that, right? But with aluminum or indium, you could do it. Okay, so it actually, these things actually do work in certain cases. Now, the last overhead, one of the last overheads I found, so I might use those, is this one. This is basically chip on board. Those little tab pieces that I handed out to you, if you're trying to, this is the tab tape, and they might encapsulate it in some sort of polymer, as far as that goes, to protect the chip. But here's the tab tape. The interlead bonds have already been made, and then you come out here to the outer lead bonds, and this is this piece of tungsten or molybdenum hot bonder that comes down and makes the solder joint. It squeezes these things together. Okay. Again, that I believe is in the chip to package interconnection handout. So that finishes up just because I finally found where my old overheads were of some of these pictures. The next thing, we went to adhesive bonding, and I pointed out that adhesive bonding is unique among all the joining processes because it doesn't really remove the surface contamination. You still have the water vapor, you still have the oxides on the surface. What you're going to do is interpose a liquid on that rough surface that wets the surface and that will essentially lower the interfacial energy. Because of that, adhesive bonding is inherently Van der Waals type of bonding. There are no primary bonds in adhesive bonding, and therefore adhesive bonding is always a weaker type of bond. If you can get primary bonding, you have theoretically 2 million, but in practice you'll get 50 or 100,000 if you get primary bonding with no residual stresses or anything to weaken it. If you only get Van der Waals bonding, you're going to be lucky to get more than 5,000 or 10,000 psi in terms of the bonded strength, because you're still going to have defects of the interface and things. Okay, so adhesive bonding, by its very nature, doesn't remove the surface contamination. Means it's Van der Waals, which means it's always going to be relatively low strength. And people that claim they're going to get 50,000 psi out of adhesive bonding are just dreaming. They're fighting fundamental chemical bonding strengths. However, we talked about 2 different types of adhesive bonding. Type 1 adhesive bonding results from attractive force of a wetted liquid against the interface. And I passed around the Johansen blocks, and you could see how, just a little bit of liquid will bond things. If you've ever had a drop of water on a table or something and put a piece of plastic on it, you can actually feel kind of the adhesion of that little piece of plastic held there by the water that's there. We're going to talk a little bit more about how you can do that. Now, there are some particular applications where, well, let me go first to type 2 bonding. Type 2 adhesive bonding is basically mechanical interlocking, and it's the one that we use most often in adhesive bonding. One example of something that's fairly pure type 1 adhesive bonding is the adhesive that you use to put the rear view mirror on the windshield glass of your car. That glass has a very smooth surface. There's no roughness there. Okay, in fact, if you put roughness in the glass, you're going to be introducing a potential crack starter. So they actually have an adhesive there that is primarily type 1 adhesive bonding, as far as that goes. And we'll talk about how you get it to be stronger than just a liquid in a little bit. We talked about wetting angles, contact angles, Young's equation. I didn't tell you at the time, but in general, well, some books will say if something's less than 90 degrees, it's wetting, and if it's greater than 90 degrees contact angle, then it's non-wetting. So basically what they're saying in such pure scientist books is that from a theoretical point of view, they'd like to say that that's wetting, this is intermediate between the two, and that's non-wetting. Well, it turns out, unless this angle is less than 30 degrees, from a practical point of view, not just because geometrically, to some scientist who has never made a joint in his life, you could never make a weld or an adhesive bond with something that has 90-degree contact angle. It's going to beat up on you. The adhesive won't flow. In fact, even at 30 degrees, it's pretty marginal. Usually you want something less than 10 degrees contact angle. And if you go back to Young's equation, which is what? Gamma solid vapor equals gamma solid liquid plus gamma liquid vapor cosine of theta. If this has to be less than 30 degrees, it puts some constraints on what these other three things are, certainly the ratios of these three. Okay? So it's nice to have a solid vapor, a very high value of this, in order to get a low value of this. And that's why metals are the easiest things to wet in general. Now, we're talking about adhesive bonding. The metal is not necessarily the surface that's being bonded to, because it's usually already contaminated with oxides and whatnot. But when we use Young's equation, when we get to soldering and we clean off the oxide, or brazing, then it turns out metals are the ones that can produce the strongest solder joints or adhesive or braze joints, because you do get rid of the oxide. In fact, when I'm doing adhesive bonding, I never really adhesive bond directly to the metal. There's always some interlaying oxide. So I'm usually adhesively bonding to some sort of ceramic. Okay? It's going to be covalently or ionically bonded. In most cases, it's also adhesive bonding is this type 1 or type 2 mechanical interlocking. And we do a number of things to try to convert the surface to a very rough surface. And there's two reasons for doing that. One is rough surfaces wet more readily. And the reason for that is relatively simple. If I had an atomically smooth surface and I put some liquid on here, the amount of high energy surface that I've reduced the energy of by creating some interfacial bonds that have a lower interfacial energy than the original surface energy is equal to this area, right? If I have a rough surface with the same width, the actual surface that I've reduced the surface energy of by interposing this liquid which wets the surface is much greater. So just on an energetics point of view, I've reduced the energy of the interface here more than here because I've got more surface, real surface area. And it turns out this is true sometimes in adhesive bonding, but in soldering more often than not. If you have some solder that just doesn't want to quite go with the right flux, if you sand the surface and roughen it up, you may find that it flows very well. Or alternatively, you can sand it in one direction and then you can put your solder drop on it, everything can be symmetric, and you'll find it flows preferentially in the longitudinal direction, the sanding direction, because of this surface roughness argument. Okay? And if you can quantify it, and you've got a handout if you're really interested that goes through the math to quantify that extra reduction in surface energy by interposing this liquid. But in order to roughen up the surfaces, typically, and I already mentioned, I think one time my oldest son's Eagle Scout project, where we had galvanized steel where the paint was peeling because they hadn't put on a primer. But to really do it right, I forced my son to research it, and we found that if you put acetic acid on the bare galvanized steel, you actually form a zinc acetate on the surface. Now, you're not always painting galvanized steel, but more commonly you might be painting iron, in which case if you phosphate the surface, or you might be painting, iron or stainless steel where you chromate the surface, or aluminum where you anodize the surface. And when you anodize the surface, you're growing an oxide. And it turns out the oxide scale looks, when you when you look at the surface of how the aluminum oxide grows, it actually grows in little cells on the surface. And as you keep on getting a thicker and thicker anodized layer, these little columns of aluminum oxide grow from that. And you grow thicker and thicker, and you actually get kind of honeycomb type of structure with all these little fingers sticking out. It has a very, very high surface area. It's very porous, and it makes a great mechanical interlocking surface. You've got the aluminum oxide bonded chemically directly to the aluminum, and now you put your adhesive on there, and it sticks because the adhesive hopefully has a wetting angle that allows it to go down into those pores, and you just can't get the thing off. That's exactly what happened with the zinc acetate, my son's Eagle Scout project. When they painted it, you can't get that paint off. You know, you're going to be down to bare. You're going to be scraping metal before you get paint off that nowadays. You phosphate steel. In fact, I didn't bring it, but people learned just after World War II that you can apply a phosphate coating to steel, and all you have to do basically is stick it in Coca-Cola, okay, or Pepsi-Cola, because I already taught you that they're basically just phosphoric acid, right? So you stick it in there, and you'll get a rough surface that grows on the iron, and that will help the iron adhere. It will help paint or some other coating adhere to that by mechanical interlocking. Yeah.
You have to make sure there's no rust or oxide on the
You got to. It should be clean because you're actually making an iron phosphate on the surface. So if you already have iron oxide on the surface, the iron phosphate's not going to form in preference to iron oxide. So yeah, you have to basically clean it and then stick it in the acid. So it's got to be a relatively clean steel surface. You can't just put it over the heavily contaminated, rusted surface. You can put chromates on. The problem with chromates, and you can put the chromates on the aluminum surfaces too. The problem, anybody know the problem with chromates? It's basically an environmental one, and it has to do with doing it. You're doing it in a chromic acid bath, which is a carcinogen. Okay, so it's the same type of thing we talked about, plating of bumpers. But people still use chromate conversion coatings. They were spec'd many years ago. They have excellent corrosion resistance. They also help with paint adhesion, so far as that goes, or other adhesives. Now, it turns out that sometimes people are confused about anodized aluminum coatings. And one time, 15 years ago, first time I'd ever been on Cape Cod, it was in the middle of a snowstorm, and I was going down there because some guy in Boston, I think it was an MIT alum, had called me up because his sailboat that he just bought the year before had these anodized aluminum rails. He was getting white spots, kind of little pits beginning all over the rails, and these rails had been built into the mahogany thing beside it, underneath it, and you know, to take this apart was going to be half the cost of this 40-foot sailboat. So he wanted me to go down and look at it. So it turns out I was down in Rhode Island anyway, so I went over there. It just happened to be in the middle of a snowstorm. And I went to look at it, and it turns out, sure enough, the whole surface of this thing was fairly uniform, pitted. It was, sometimes you call it white rust, but basically it was forming its own little aluminum oxide, and these were going to turn into pits. And the problem was, whoever had done this, I don't know, I never tracked down the details, but when you anodize aluminum, if you want a porous surface, then that's all you do, is you anodize it. You don't bother to seal the surface. If you want corrosion resistance from an anodized aluminum surface, you have to seal the surface. Because, let's face it, this thing has got channels all the way down to the aluminum metal. It's not a continuous coating that's going to protect you. And in fact, it has to be. If you think of how anodizing goes, I put it in a bath and I apply a current. Well, how can I be applying a current and growing something unless there's a conducting path? And so that's why these cells actually form. I have a path of liquid, conducting path, and then I grow the anodized layer in between those little cells of liquid, right? So inherently, it's going to be a porous surface. Great for painting or adhesive bonding, lousy for corrosion resistance. In fact, it just gives you a perfect kind of surface to start getting pits formed. What you have to do after you've anodized aluminum, if you want to anodize it for corrosion resistance, you have to seal it. And you seal it by boiling it in hot water. Okay, you don't apply a current. Just boiling it in hot water will help grow the oxide in between these cells. So you fill in the cells by just corroding it in hot water. Okay, so that's called sealing the aluminum. They also sometimes seal it in sulfuric acid, in hot sulfuric acid and other things. This is just a plot of, oops, that's a plot of crackling. Why did I do that? Oh. Crack length versus, I don't remember what that graph is right now, so don't worry about that graph. But anyway, I wanted you to see the porous nature of that. So we do lots of things to roughen up these surfaces. Now, phosphating of steel was first discovered not for painting right after World War II, but for lubrication. And I should have brought it in, but I'll bring it in Monday if I remember. If I want a lubricant to adhere to the surface, I'd love to have a porous surface that would hold the lubricant. So if I anodize the surface or I phosphate the surface to get this rough surface, the adhesive will be held better. And so, for example, actually I learned this in my doctoral thesis. I was drawing niobium wires and I was using molybdenum disulfide rather than graphite. Remember I said molybdenum disulfide has the same kind of crystal structure, and graphite's the lubricant when it's got oxygen on the basal planes. Molybdenum disulfide has the same crystal structure. It's excellent solid lubricant, but it doesn't always adhere well. And I tried to draw the niobium with the molybdenum disulfide, and it didn't work very well. And I learned that I needed to anodize the surface of the niobium. And you get this beautiful, anybody see titanium jewelry that's been anodized, and you get blues and oranges and yellows and stuff? A few years ago it was popular to make earrings out of it, kind of rainbow colored earrings. That was just anodized titanium, where they anodize it with different voltages. Actually, in that case, they're probably just slowly taking it out of the bath to get the rainbow of colors. And the thickness of the anodized layer, when it's a quarter wavelength of the light, will reflect the light that way. And so as you get different thicknesses, you can get different colors. So medical instruments, titanium medical instruments are often anodized blue, because titanium forms this nice cobalt, or kind of royal or cobalt blue. And I asked the people at Division of Johnson & Johnson once why they made them blue rather than some other color. They said, because Dr. DeBakey likes it. Okay? You know, the famous heart surgeon. But anyway, he liked the color, so that's why they made them that color. But actually, sometimes they color code titanium instruments by just, in fact, screws that go on your back. Some of them are blue. One length screw is blue and one length is gold. Okay, and they just do it by anodizing them at different voltages to get different thicknesses of these things, and that means that the surgeon and the nurses don't have to worry about measuring the length. Okay, they can just see it's color coded and it's stuck on there. Well, for my thesis with niobium, I ended up taking these wires and I would just stick them in. I didn't use Coca-Cola, I used sodium hydroxide as electrolyte. Didn't really matter what you use. I would grow this nice blue anodized surface, and I put the lubricant on there, and it drew, you know, I could pull it through the wire drawing dies beautifully, because now the lubricant was adhered to the surface in these porous surfaces. Going back to the iron phosphate, what they learned in 1946 was that you could phosphate the steel and use calcium stearate, which is otherwise known as soap, okay, fancy lubricant. And they put the soap on the surface, and they could cold form these pieces of steel, and the lubricant would keep smearing out all around the surface, because now I have a thick layer of lubricant. I didn't just have a thin layer of peanut butter, which if I got too much deformation, it would start to weld to my tooling. I now had a thick layer of peanut butter, and now I could stretch it out a lot further into forming it without it wearing against the tools and welding to the tools. Again, lubrication is kind of the opposite of welding. And so they developed what's called cold heading, and I should have brought the parts, but I have a little part that if you've ever put together one of these cheap computer desks from Walmart or Kmart or something, it's got these little metal inserts that go into the particle board, because you can't put any decent screw in the particle board. So you have these metal inserts that lock into the particle board, and then you put basically a metal screw into that. Well, I have one of those those parts are cold-headed. They start out with a rod of maybe half-inch diameter. Actually, I think this one might be 3/4 inch diameter steel. They shear it off. They come in, and at room temperature, they just slam it with some tooling, but they had to phosphate it at first. In fact, the part I had, you used to be able to feel the soap on it, but it's been passed around the class so many times that the soap's kind of worn off. But it used to feel soapy because it was a phosphated steel part with this calcium stearate on it, and that would allow them to slam it once and then slam it again. So there are like 7 different steps to make that little part, and there's essentially almost no scrap. And they do all kinds of parts. I mean, most little metal parts that you see are coming out of these cold heading machines, which are almost, they kind of go 3 or 4 times a second. Type of banging rate of forging, cold forging these little metal parts. Never could do that until they understood how to prepare the surfaces. Okay? To adhere things better to the surface. Any questions on that? No. Let's go to the Stefan equation, which is, pardon me? What's oh, not that Stefan. This is a different Stefan. However, this is the same as the Stefan Boltzmann constant. Okay. It says that the force time product, a wetted liquid between 2 flat plates. Now, I'll give the John. So basically, what Stefan was, let's say I had a liquid between 2 solid plates, and I'm going to squeeze the plates together to flatten that liquid between 2 plates. Viscous liquid, and so eta is the viscosity, H initial is the separation between the plates initially, and H final is the final separation. If it's a circular disc, that's the radius. That's the Stefan equation. What he solved a number of years ago was, what's the time it takes to squeeze a liquid between 2 plates? If you want the derivation of it, you can go to a book, although you can probably only find this in the MIT library. J.J. Bickerman. Of adhesive Bickerman was actually a professor of civil engineering here at MIT, and he wrote a book on it. I guess he had to worry about how to glue houses together or something. None of the modern books on adhesives go through this. Now, I found some people at Sandia Labs in the last 5 years who have rediscovered the Stefan equation and how it applies to adhesive joints. But for something like 20 or 30 years, it seems like people forgot about this is how it really and throwing them away. You got a bunch of physicists who were told by some manager, you're supposed to work on adhesives, and they went off and worked from a fundamental, worrying about the gluons holding the quarks together and things like that, for whatever that's worth, which is essentially nothing. About because it's fun. If I put it, which is atmospheric pressure, I'm going to give you 3 examples here. 1.4, which is a tenth of an atmosphere. 1.4. Put in some values for water. 10 is more like syrup, as far as that goes. If I've got a diameter, or one that's 10 centimeters, or one that's 10. I have H2, which, well, H2 is H final. Yep. H final, which is 0.1 centimeters. 0.1 centimeters is 4/10 of a thousandth, about a half thousandth of an inch. Or 0.01, you're getting down to a few tenths of millionths of an inch. A really good fine surface finish. And I'm going to start each one at a tenth of a centimeter. And I want to know how long it takes to squeeze that liquid together. It takes 7.5 milliseconds in the first case. It takes 75 seconds in the second case, and it takes 7,500 seconds in the third case. You can figure this out. I'm plugging these numbers into the Stefan equation to give you some examples. So with atmospheric pressure, water is the liquid, a little disc 2 centimeters in diameter, something half a thousandths final separation. Not all my surfaces are that fine. I can do this in 7.5 milliseconds. If the size, I square this, things go up by a factor of 100. If I drop the pressure, it goes down by, or the time goes up by another factor of 10. And then what else did I do? I did something, I changed the viscosity, so I got 10 to the 4th, okay? But this is basically just something that's kind of like syrup. So yeah, this is a little bit bigger area. The pressure's down to a fairly low pressure. It could take a long time. This last one, I just made things even thinner here. And since that goes as the square, you get to ridiculous times to make the bond. Now, why should you have to worry about trying to make bonds in 7.5 milliseconds? If you went to the store and you were thirsty, and you are actually these are not adhesively bonded. Your orange juice containers have labels on them, right? But if you take a beer bottle or something like that, they put labels on them, right? Or you take a relish jar or a mayonnaise jar, right? They've adhesively bonded a label on there. And when they're filling these things, anybody have an idea how fast they fill beer bottles or soda bottles? 24 a second. A case a second. Basically have this big lazy Susan table, it's about 10 feet in diameter, and the bottles come feeding in, and they get filled as they go around the table, but they're coming out at 24 a second out of that thing. They're actually in there for a couple of seconds because you can fill a couple of cases around the circle. But the machine squirts it in. In that process, they also have to slap the label on. So you've got to be able to slap the label on and have it bond within a fraction of a second, maybe not 7.5 milliseconds, but you've got to have an adhesive that doesn't take long to stick, okay, and form. You can't just, if it's a viscous liquid, then you've got to form a thin joint. What does the Stefan equation tell me? It tells me that as the joint gets thinner and thinner, the bond or the force time product to squeeze this together is going to get longer. The interesting thing is the Stefan equation also works in reverse. If I went back to the differential equation that solved to get that equation, if I start out with this as the initial and this is the final, I will get the exact same equation. It's just to reverse these, right? So now I can say, if I have a viscous liquid between two plates, I want to know how long that joint will last, because the viscous liquid has got to flow, right? In order for these, if they're already wetted, there's going to be a certain, depending on the force I apply, how long will it take to separate? Well, if I go back to this, and I had something with a viscosity similar to water, or maybe my Johansson blocks had a little grease on them, so the viscosity is a little higher, and I get a slide them together and make them really thin, and I have some force, which maybe isn't much more than about 1.4 psi, the Johansson blocks might hold together for 7,500 seconds. And in fact, if I had stood there and held those Johansson blocks sometime in the next minute or two, they probably would have fallen apart. Because it's just a viscous liquid that's holding them together. And the viscous liquid will flow with time, right? So you can look and you can see what the parameters are. If I want to have a good adhesive strength and last for a long time, this product has got to be large. And one of the secrets in adhesive bonding is to start out with something that you can form very quickly, like slapping a label on a beer bottle, and have it change some way such that it lasts for a long time. And what do you change? You change the viscosity, right? If you look at it, you can't change the area of the bond. You can try to make a thinner and thinner bond, and in fact, you've experienced that, because if someone puts something up on the wall with Scotch tape or something else, and you come back 5 minutes later and it falls down because the adhesive wasn't very good, what do you do to try to make it stay up longer and harder the next time? You go and you push on it real hard, right? All you're doing is increasing the force to try to increase the force time product to get this thing smaller so it stays up longer. But still, all you're doing is type 1 adhesive bonding with a viscous liquid in between. The problem is every time it falls down, you put it back up, you're picking up more contamination, and so the actual bonding strength gets worse and worse each time. But you basically are squeezing harder and harder. When I'm bonding beer bottles, I'd better have a very, very low viscosity adhesive, or I'm not going to have time to slap that label on there. Okay. However, once the label's on there, I want to change this to a very large value. And in fact, how much does viscosity vary in the world? Anybody have any idea? I mean, viscosity is measured as a shear, right? I apply a force. I apply a force to something, and over time it creeps. Okay, so you apply shear stress, and that is the viscosity is the proportionality between the shear stress and this displacement versus time. So it slides, viscous, right? So it moves with time. So it's a dx dt. It's how fast it moves, some velocity. I apply some shear stress and I get some velocity, and the proportionality is viscosity. Well, it turns out the viscosity of a gas is something on the order of 10 to the minus 3 gram centimeters per second, per centimeter squared. Okay. Viscosity of water is about 1,000 times greater. Yep. Yep, the units of force here, they should be in PSI, I think. Did they not work out? Right, this is just force over area. Well, you can, except you just if you bring the a squared over there, I'm just writing it down like Bickerman and everybody else does. So force over a squared is pressure that I apply. Okay? I think that it's been a while since I worked this out. But you have a homework problem and the students haven't complained too much, okay, about getting the units to work out. But I mean, if I have a larger area, then it takes a greater force to break it. So I'm just talking in PSI to break the force per unit area, right? Okay, so I want to change the viscosity. The viscosity of a gas, gases are not very good adhesives, okay? They're pretty good lubricants, I mean a gas bearing, right? But water's about 1. Molasses might be 100 or 1,000. A solid is something on the order of 10 to the 10th. It might be 10 to the 8th, it might be 10 to the 14th. Some solids are harder than others, right, in terms of their ability to resist force over time or creep. Lead, obviously, is a much lower viscosity than steel, which is lower than tungsten, okay, which is lower than diamond. It turns out at some point you run into a problem of trying to measure things. Supposedly the highest viscosity ever measured was when Professor Orawan, who was a famous professor of mechanical engineering here, estimated the viscosity of the Finnish coastline. Okay, and apparently for some reason geologically he had learned that he figured he could apply he knew some force had been applied to the coastline for eons and eons, and he estimated from the rocks what the time was. So he has this force divided by this very large time, and he was able to estimate a viscosity, an effective viscosity of the coastline of 10 to the 22nd, for whatever that's worth, okay? But in practical sense, you can vary this from the adhesive viscosity of the liquid, which might be 1 to 1,000, to the adhesive viscosity of a solid, which can be 10 to the 10th to 10 to the 13th or 14th. 10 orders of magnitude. So what does that do to this? It increases this product by 10 orders of magnitude. So if I form the joint within a second, that means that if I solidify the joint, the adhesive, the liquid in between, it still is going to fail, but it's going to take 10 to the 10th times as long. Now, how long is 10 to the 10th in years? A good rule of thumb is 1 year is about 10 to the 8th seconds. I can't remember if it's 2 or 3 times 10 to the 8th, but anyway, it's on the order of 10 to the 8th. So you're talking 30, 40 years for the adhesive joint if you get a 10 to the 10th increase in viscosity. So all you have to do is solidify the adhesive, and Bickerman's or Stefan's equation still works. Now, that basically takes you to the idea of why do I, or how do I make adhesive joints? And we'll go over Monday, but there's 3 basic ways to change a liquid into a solid. What's the first one? What's the most obvious way to change a liquid into a solid? You freeze it, right? You know, freeze water and turns it into a solid ice, and you've changed the viscosity by, maybe in that case, maybe only 8 orders of magnitude, but so what, okay? What's another way? You could increase the pressure, however, and the pressures you have to do are huge pressures, thousands of atmospheres. That would work, but that's not one of the practical ways that we do it. Right, if I can dissolve something in a solvent, if the solvent evaporates away, I can end up with a solid left over. And that's basically a postage stamp, is solvent removal, okay? You just put the solvent on, all right, you lift the stamp, that's the solvent. It started out as a solid glue, and you dissolve it, you put it on the paper, and the solvent, the water goes away, evaporates away, and it re-solidifies. But now it's interlocked down in those pores of the paper on the envelope, right? And the last one, I can basically do a chemical reaction. I can take epoxy, and I take these 2 things, and they can have a chemical reaction, and they can solidify because of the chemical reaction. So the 3 basic ways, and we'll go over those and talk about different examples. In fact, as your homework for the weekend, think of any adhesive, whether it's, you know, you're making a ham and cheese sandwich, and you're putting some mustard on it, and you're looking at the bottle, something's adhesively bonded here. And you're going to see all kinds of things that are adhesively bonded, okay? In fact, if you have an asphalt driveway, it's adhesively bonded rock, okay? And how did they adhesively bond it? If you got bricks in your house, it's a mortar, okay? The mortar, how did the mortar go from being a soft, quote-unquote, liquid that you could deform and get it to go into the pores of the brick and then harden up, okay? So just kind of over the weekend, think of anything you see that's adhesively bonded, try to say, well, did I solidify it, did I react it, or did I take away a second component? Did I do solvent removal to get it to harden up, okay? So we'll see you on Monday.